So let's look at the op-amp circuit. I already connected that for the example we did. The example has the inverting amplifier has the R1 1 key and R2 10 key, and the capacitor is 0.1 micro. So I'm using the exactly the same parameter here in the op-amp circuit. And what you're looking at here, if you remember, this is the LM324, and it has 4 op-amps inside this. This is a notch here. This is a notch, and we count the pins counterclockwise, starting from 1 here. Right, this is the number 1 pin, and we go 2, 3, 4 until 7, and 8, 9, 10, 11, and there are 14 pins. So 7 on each side. And I'm biasing this one with -12 and +12. So the power, the plus side, this red one here, connected to pin number 4, and the -12 connected to the pin number 11. And I have all the grounds. I'm using this negative rail here. I checked and made sure there is nothing connected there, because this board could be powered. And so in this case, I'm having all the grounds, including the ground of the source. That's the ground of the source. I believe this black line here, this coming is for the ground for the source. And also I have the scope grounds, and also the function generator grounds. I'm going to use this to generate the yellow line here. That's going to be generation of the sinusoidal signals. And that actually is sending this signal through this 1 kilo ohm resistor, and this 1 kilo ohm resistor connected to the inverting terminal, which is number 2, and then I have the 10K, the little resistor there. I have a 10K, this one here, and it kind of blocked by the, so this is a 10K by this this wire here. Let's see. So this is a 10K ohm resistor, and this little electrolytic capacitor. I'm having a really small voltage. I think this positive and negative doesn't really have very small current, doesn't really destroy the capacitor itself. So let's see. In this case, we calculated we have. So I would like to check a few frequency points, and the frequency at this cutoff frequency, which is 1,000 reading per second, right? So 1K, that corresponds to this wave generator I'm having here is given in terms the hertz. So if you divide that 1,000 by 2 pi, will give you roughly 159.15 hertz. So this is the AC signal I'm giving. And in that case, the output should have the amplitude should be the based on our approximation. Let's see. So in this case, close to 20 dB. Remember, it should be 20 dB minus 3. So that corresponds to 10 times. So that 20 dB is 10 divided by square root 2. That's equal to I think it's 0.707. No, 7.07. 7.07. So this is the output voltage. We should getting close to that 7.07 if our circuit working properly or our calculation correct, right? So let's see the output, read the output, and also remember the phase angle. The output should be leading the input by 135 degrees. And let's see. So I have the reading from the measurement, and so in this case, the input is not exactly 9.5. So in this case, I should the output should be so 9.5 divided by times 707, right? So 9.5 times 0.707. So that should be 6.7. So I got a 6.3, pretty close right there. maybe multiple reasons for that, because the resistance and the capacitance, all the values, they have the errors there, so they're not exactly the same. And also the capacitance, the frequency dependent. At each frequency, this electrolytic capacitor will have different capacitance, so on and so forth. So, but we are getting quite close, right? Let's see if we reduce the frequency to 10 times below this corner frequency, that we will see much higher. I hope we will see almost a 10 times, that the output should be almost 10 times of the input. So let's see. Let's change the frequency to, just by moving this decimal point to the left, so 15.9 hertz. So in this case, I need to change the base. I couldn't see this, so you change the base to 10 milliseconds per division, and you see the channel 2, which is the output, where I connect the blue curve now, has almost 10 times, right? So I have 9.2 output, I have a 10. So here, this is the 0.95. So this is very close to 10 times. And you see the phase angle, right? The phase angle almost 180 degrees. That's very close to what we predicted. So it's slightly off a little bit, because the actual one, remember, the actual plot is something like this. The actual plot is something like this. I need to reconnect. Okay. So this is not. This is the example for first. Yes, the actual plot is slightly below 180, right? So therefore, we have that. Phase angle quite close also. And let's look at above this corner frequency 10 times. So in that case, we're gonna need move this to 100 times higher. So we got a 1591.5 hertz. So in this case, they changed the 1.9 kilohertz. That should be correct. So in this case, I need to change the base 100 times smaller. I have using 10 milliseconds. I'm going to use 100 microseconds per division. So in this case, the output here, so now it's a little bit confusing, right? So right now I'm using the different scale. So for the input of the orange one, I have the 1 volt per division, and for the half volt per division, I'm sorry. And for the output of the blue one, I'm using 2 volts per division. But look at the reading here, right? So now the output and input are almost the same. That means the gain is almost 1, right? So that's the almost close to the 0 dB at this 100 and this 10K reading per second. So 1.5 kilohertz. And if you go higher frequency, that means the output even will be even smaller, right? So let's just see that. It should be, by the way, the phase angle, before we do that, just pay attention to the phase angle. The phase angle should be close to 90 degrees. The output leading by 90 degrees. Let's see that. It's pretty close, right? So the peak value of the blue one almost occurred at zero crossing of the orange one, which is, so that close to 90 degrees. And let's do another one and increase this further by 10 times and see this low pass filter effect, right? So in this case, the signal will be further attenuated by 20 dB, which is 10 times. So I'm expecting the output would be almost 10 times smaller than the input, right? So in this case, I may need to change the scale so that we can see that. So in this case, you see this reading is really hard. So I'll change the range to. So let's see, change it maybe to 20.2. Yeah. So in this case, the amplitude is 90 millivolts, right? For the input, I'm reading the measurement here. I have no idea why there is this little glitch there. There looks like some distortion. So let me using the different time scale also. So let's see, maybe 10 microsecond per division. So I have no idea what this distortion, where this distortion comes from, because it doesn't seem to. Maybe the capacitance is not ideal anymore. I'm not exactly sure, or maybe something with the circuit. But here you see the reading is still correct. If you have other comments, and leave your thoughts in the comments area. See, I have no idea what is happening here. But at lower frequency, we didn't see this, right? Or maybe the op-amp circuit maybe not working properly. I'm not exactly sure. Or maybe there are too many things. It looks like there's a resonance there, right? But this is the interesting part of doing the actual experiment. You won't be able to see this in simulations or in the plots in the textbook, right? I hope you enjoy this. You just observed this actual circuit working here. Although not at a high frequency, I have no idea. There's a little bit of oscillation. I have no idea where that's coming from. But you saw this circuit, right? So I hope you enjoyed the video and this video clip that I have for this lecture. So until I see you next time, remember, keep going no matter what you do. Just never stop, okay? I'll see you next time.